Okay, one of the fundamental concepts of projectiles is that the vertical axis, what happens in the y, is independent of the horizontal axis, what happens in the x dimension. This little simulation shows that. The acceleration vectors are shown there. The acceleration in the y is, rounding it off to 10 meters per second squared for both the red and the green object. Now, in our first situation, we're just going to drop them side by side. I have taken away air resistance, so there is none. When we drop them side by side, that means they will fall side by side. Now, most people at this point don't have a problem with that. As long as both objects are not particularly light, you can see that for each leftover picture, they're in essentially the same place that they were before. Now, they're at the same height. They've fallen the same amount of distance. Again, distance in the y, s, would be equal to 1/2 of gt squared. G is the same for both, so at any given time, they will have both fallen the same distance. What most people don't believe in is the fact that if you should project one of them horizontally, throw it to the right, directly horizontally, they will still be at the same heights as they fall. The fact that you're increasing the velocity to the right seems to make everybody think, well, the thing is going faster, therefore they can't possibly be falling at the same rate. Again, the key point here is that there's only one force, that's the force of gravity, that causes the object to accelerate only in the y direction. What's happening to the ball in the horizontal direction has nothing to do with the rate at which it falls. So I'm going to maximize the speed. I'm going to go to 10 meters per second to the right with the green ball. Instead of being projected or just dropped, it now has a horizontal velocity. It now has an initial velocity in the x direction. It has a ux. But notice it still does not have a uy. I'm not saying I'm throwing it downward or upward. I'm saying that I'm projecting it in the x direction. Okay, so when I do that, if you look at each situation, in the first place, they started from the same height. At the next time interval, both are ball positions are plotted at that time interval. They are still at the same height. In this next one, they are still at the same height. And the next one, they're still at the same height. And ad nauseum, the height is not impacted by the fact that the right one now has the velocity. Notice that it is a constant velocity because there's no force in that direction. Since the summation of forces in the x is 0, the object must move at a constant velocity of 10 meters per second. Now, if we change the speed, we bring the speed, say, to half of what it was before, about the middle of the other two, we get the same basic impact in that in terms of the vertical, they're still exactly the same. For all the situations I try here, the vertical is going to be exactly the same. Now this time I have a slower speed in the x, so the ball did not travel as far to the right. But they would still reach the ground, assuming a level surface, at the same time. So, if you were to shoot a bullet from a gun and drop a bullet at the same time, they still will reach the ground at the same time if you do that experiment with a level gun, horizontal, and over a level surface. It's hard to believe. You think, wow, that one has to spend more time in the air because it's traveling so much farther downrange. But the speed at which it's traveling downrange has nothing to do with the amount of time that it takes to fall. So a dropped bullet will hit the ground at the same time as a shot bullet over a level surface shot from a horizontal gun. So independence of axis is very, very important. You have to get over that common misconception that because the ball is traveling now in the x direction, it must take more time to fall. Doesn't matter what happens in the x. It has no impact on what's going in the y. They are totally and absolutely independent of each other.